Let's start with Socrates. Now, the Greeks did not do science in the modern sense of the word. They practiced philosophia naturalis, or natural philosophy, which can be roughly described as the rational inquiry into the principles and causes of the natural world. You might say, that sounds a heck of a lot like science. Well, yes, but the primary element missing is the idea of empirical observation. That is, to systematically and carefully test our ideas and theories about the workings of nature in an experiment. Natural philosophy is like a precursor to the modern scientific practice. But this guy, Socrates, he wasn't even a natural philosopher like the other Greeks you may have heard of. Then what is he doing here? It is because he advertised something incredibly important for gaining knowledge and seeking truths almost about anything. Questions. A lot of questions. You will probably hear the term rational debate or the Socratic method more often, but the core idea is the same. That is, to ask a sequence of well thought out questions in order to confront one's ignorance about his knowledge gaps and the presumptions involved, ultimately making progress towards a better understanding. And in science, questions, and especially posing the correct questions to poke at the conundrum or the problem at hand, is far too essential for progress. The impact of Socrates can also be seen through the works of his students, Plato and Plato's students Aristotle, both of whom wrote a lot about their ideas and theories of nature. However, the idea of systematically testing the theories or to base the theories off of carefully conducted experiments really took prevalence after Al-hazan ibn al-haytham. Roughly about 1,000 years ago, Ibn al-Haytham investigated light and published his ideas in the revolutionary Book of Optics. He is considered the father of optics for this work, but apart from revolutionizing optics, Ibn al-Haytham and his Book of Optics also revolutionized the practice of investigating the workings of the natural world. He not only laid out his ideas and principles of light, but also how he arrived at those conclusions in his investigations. He wanted people to be able to wield his methods and reproduce the results of his experiments and not just take his word for it. And for that matter, anyone's word. This will eventually become a key idea of the modern scientific method. Nullius in verba, on no one's word. Which is to say, don't believe something just because someone else tells you it's true. Test out each new hypothesis or educated guess yourself. And this goes not only for ideas that you may hear from someone else, but also that you may yourself come up with. Say you guessed at a theory of some natural phenomena. It is not enough that you only report the observations and the conclusions that you draw from them and ask the reader to better believe them. No, the reader and you, the scientist here, you guys should be able to check each other's work, that the proof, for the lack of a better word, of the phenomenon under study should be something that can be reproduced. Let's take the example of Jeff. It is important that Jeff gives as much detail as possible for how he conducted the experiments and did the calculations or the statistical analysis of the experimental data such that there is a prescription, a procedure per se, for reproducing the results. A prescription that anyone can follow. Back to Ibn al-Haytham. His book, The Book of Optics, was eventually translated into Latin after a couple of centuries, which allowed it to become relevant in Europe and had a lot of impact on how to do science. It is not an accident that people like Roger Bacon, Galileo, Kepler, Newton, Snell, and many more of the notable personalities of the subsequent centuries in Europe had either read Ibn al-Haytham's book or had direct or indirect links to his work. With the addition of the ideas of Galileo, Francis Bacon, and René Descartes, and more guys of this period, these approaches culminated to investigate into the workings of nature, the pursuit to find out how the universe works. The scientific enterprise had developed the modern scientific method. Suppose there is some natural phenomena that we want to explain or study. We observe the phenomena and then try to form a hypothesis, a theory to explain it. You can call this a guess. Then we see how our idea plays out, what it predicts. That is to say, we compute the consequences. We do this to check the validity of the guess, and then we devise experiments and conduct them to test these implications. We compare the predictions of our hypothesis to the nature with the experiment, and thus comparing it directly with the observation. If it disagrees with the experiment, there is something gone wrong. Now, that wrong can be at any stage. Maybe you set up the apparatus wrong, or maybe your calculations were incorrect. Or perhaps what is most likely when you are trying out with a new crazy idea is that the theory that we are trying to test is itself wrong. This is kind of the key to science, that experiment is the sole judge of truth. If experiment disagrees with the prediction, there is something wrong at some stage, and further investigation must be done to evaluate where this wrongness must be occurring from. If you can find nothing else, and you are very careful with your observation, then that leaves you with the one possibility that the hypothesis that you are trying to test is itself invalid to explain the natural phenomena, as it does not agree with experiment. Experiment is the sole judge of truth. As Feynman puts it,
it doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
One thing to note is that your hypothesis or your guess, it doesn't matter where the guess comes from. What matters is that it is definite so that it can be tested, and it should agree with the experiment for it to be established as a theory. Notice, however, that from the scientific method, if we have a definite theory with a definite prediction to test it on, then we can prove it wrong, but we cannot prove it right. Even if the theory passes the test, the results of the experiment came out as predicted by the theory. It is not a proof of the correctness of the theory. The best we can do is say, we haven't found it to be wrong yet. Because to say that a theory has been proven correct would be to say that all the predictions of the theory for all the cases has been tested and verified, and all future experiments of the theory will also only yield confirmations of the theory, which of course we do not know. We cannot know. And so we try to guess at the most likely explanation, keeping in the back of our mind that if it doesn't work out, then we must discuss other possibilities.